Hi, everybody, and welcome to week 2. So congratulations on getting through the first week of classes. And this week we're going to take some of what we learned about geography and apply it to climate. Now, in the second lecture, we learned about latitude and longitude, and a lot of what we'll talk about today relates to how Antarctica's specific latitude actually affects its climate. But before that, we will talk about solar radiation and how that drives Earth's climate to begin with. Everything ultimately will come down to solar radiation, aka how much sunlight is reaching the Earth. And that will hopefully help address the questions of why is Antarctica so windy and why is Antarctica so cold? It has to do with solar radiation, temperature, and pressure. Now, if you are just joining the class, I highly suggest watching last week's videos and reading the syllabus as soon as possible, because we are at the point where we will start building on material from the previous classes. And I can, more than anything, you just don't want to fall behind. You don't want to end up with a whole bunch of lectures piled up on you. Looking ahead to the work, this week, there is a lab due this coming Friday. There is also one of the 2 reading assignments is now available. It is not due until after the midterm. Sunday, February 14th is when it is actually due. What you'll want to think about as you go through this class is what topics interest you, what do I touch on that you might want to know more about, because that might be a good base to find a news article about Antarctica that you might want to write about. And it doesn't necessarily have to be topics that we've talked about in this class, but it does need to be Antarctica related. And we are not looking for a scientific article for this first one. We're looking for a news article. You can lose points by plagiarizing or copy pasting your summary. You can lose points by not meeting the word count, not linking your article, or if you accidentally email, or if you send it to me as an email rather than put it on GauchoSpace. But for the most part, it's a free write. Outside of summarizing the main point of the article and talking about what you had not known about Antarctica, and also what was interesting to you about that, you can more or less respond how you want to the article. And I kind of hope this is a good opportunity for people who their background may not necessarily be earth science to begin with to engage with Antarctic research a little more, because this is going to be written, because these articles are written for the general public. These articles are meant to disseminate findings about Antarctica, like news events or scientific findings, to the general public. And today's big question largely is going to be, why is Antarctica so cold and dry? And this week's big question, actually, because we'll be talking about climate today and on the lecture that I'm releasing on Wednesday. So today, the first half of the lecture will talk more, the first half, the part that you're watching now, will be more heavily about about an overview of Earth's climate. And the second half of this lecture will talk more about what that means for atmospheric circulation, and start to get into what does that mean for Antarctica? What does that mean for the climate in Antarctica? So the last thing I mention here is the Coriolis Effect, a concept we will come back to in Wednesday's lecture, but we will begin getting into the basics of that today. I mentioned solar radiation, and solar radiation is where it all begins. The vast majority of energy available to use on Earth comes from the sun, and light on Earth comes from the sun. Life on Earth depends on the sun. Climate depends on the sun. Climate is to a big extent driven by solar radiation. And when I say solar radiation, I literally mean the light coming from the sun. And remember that one reason why Antarctica is so cold is that at the poles, the same rays of sunlight, the sun is sending out the same amount of sunlight in every direction, basically. Those rays of sunlight are hitting the equator head-on. Because of the way the poles are curved, these same beams of light are being spread over at the poles and hitting them much less intensely. Aside from the flashlight example, another way to think about it is the equator is, let's say that you have a boxed recipe that gives you a certain number of cupcakes and a certain number of frosting. A certain amount of frosting. You can put frosting, all the frosting on one cupcake, or you can spread it across the cupcakes. You'll get really thick frosting if you put it all on one cupcake, and it'll be much thinner if you spread it across. The poles, for the poles, it is spread across. The same amount of sunlight is reaching them, but it is spread out. And remember, something you may have learned, something you may have come across in a physics class is the idea of light as units. Light is quantifiable. We can measure light. Light can be conceived of as a photon, as a particle of sorts, and light, there is a finite amount of energy, a finite amount of light, a finite amount of radiation. Something else I'll talk about is that the light that we can see is only one example of the entire spectrum of radiation on the electromagnetic spectrum, as it is known. I will specify what we're talking about. We're mostly going to be talking about visible light and ultraviolet radiation, to a lesser extent infrared radiation as well. Most of the solar radiation is visible light and ultraviolet light, very high energy and short wavelength light. Something else that factors into this, however, aside from the light being spread out, is the fact that Earth is tilted. One thing I really like about this diagram on the right is that it shows that when everything above the Arctic Circle, to simplify it, everything above the Arctic Circle will more or less be in 24-hour daylight. Even Baffin Island is going to be in daylight. Baffin Island is going to be in daylight. The Antarctic Circle, everything below the Antarctic Circle, is going to be in complete darkness. The tilt of Earth's axis is fundamentally what causes seasons. It causes varying amounts of solar radiation to hit a given spot on Earth at different times. Now, if there was no tilt, if Earth was simply hitting the, if Earth was simply hitting the sun head on, the poles would still be colder. The light would still be more spread out at the poles than at the equator. However, one pole would not be in complete darkness for most of the year. It would be a little more even throughout the year. And the tilt of Earth's axis is what causes the polar cold, specifically what causes Antarctica to be in complete darkness during its winter, as well as what causes the southern hemisphere to be experiencing winter during that same time. On a sort of a smaller scale, you'll notice that the southern hemisphere is going to be tilted away from the sun, and more of it's going to be in darkness for more of the day. So the southern hemisphere is in winter the same time that the southern hemisphere is in winter the same time Antarctica is. When Antarctica is in complete darkness, we in the northern hemisphere have our summer. At this exact same time as Antarctica is in complete darkness, the northern hemisphere is actually being pointed towards the sun. And that is fundamentally what the tilt of Earth's axis does. It is pointing one hemisphere towards the sun and one hemisphere away at different times of year. And what you'll see happens is that on this diagram showing Earth's orbit, it's because Earth is kind of, you'll see it's kind of, it's not going to like flip around. Earth is going to be in what we'd call spring and fall. It's kind of side-on tilted so that both hemispheres receive approximately the same amount, and hence why spring and fall aren't really that different. They just look different because you have in spring the world sort of gearing up for summer, and in fall the world kind of quieting down for winter. But that really has more to do with living things and what living things are doing than with the temperature being received. Spring temperatures are pretty similar to fall temperatures. And it is spring here at the same time as it's fall in the southern hemisphere. During spring here and fall down there, the southern and northern hemispheres are getting roughly the same amounts of solar radiation. And then when Earth has rotated around here again, you'll see it's the other hemisphere that is facing it head on because of the tilt of Earth's axis. And remember that the tilt of Earth's axis was something we talked about a bit before with the Antarctic Circle. The Antarctic Circle is defined, remember, based on the areas that receive total darkness during the winter. Earth's axis is always tilted, but varies slowly over geologic time. And that affects where the Antarctic Circle is, and thus the differences in the seasons. Now, I referred to solar radiation as energy and as light. So light is not just the light that we can see. It is energy that travels as a wave, And it may either be shortwave radiation or longwave radiation. Now, if you look at this diagram, this line on top shows you the wavelengths of different forms of radiation. It shows you physically, actually, how, well, it's simplified a bit here, but it is physically how much length there is between peaks in radiation and troughs in radiation, low points. Just like waves on the ocean, in fact. It is the same concept. It is the same concept as you have for waves in the ocean, because waves in the ocean are a means of transferring energy just through water, the same way that solar radiation is a means of transferring energy as well. Waves are fundamentally a way to move energy, and the wavelength is the length between two peaks in that energy. So you'll notice that the peaks are all really spaced together. For gamma rays and X-rays and ultraviolet, they're really bunched up together. They have a short wavelength because there's not that much difference between these two peaks. If you go to the other end of this diagram, to radio waves, you will notice that there is quite a big length between two peaks. And wavelength goes opposite to energy. If something has a short wavelength, that means it's going to be moving rapidly. It's going to be oscillating rapidly, and is going to be very high energy. So you'll notice gamma rays. Gamma rays are actually a form of radioactive decay. Gamma particles are released when atoms break down. And those are really dangerous, in part because they're so energetic, and because they have such a small wavelength, they can actually physically damage your cells and cause cancer. Same with X-rays, and hence that's why shoe stores don't let you just look at your shoe through an X-ray when you're trying it on anymore. They used to do that and then discovered that that was unnecessary exposure to damaging radiation. And all of this is radiation. You might hear radiation. Isn't radiation bad? Radiation is bad for you if it's really high energy radiation. To a less extreme extent, ultraviolet radiation, which is slightly shorter wavelength and higher energy than, you'll notice, visible light. And you'll notice visible light, the wavelengths of visible light are actually about as large as amoebas or bacteria. But ultraviolet light is referred to as such because it has a shorter wavelength and higher energy than violet light, which is the highest energy visible light that we can see. So it's past violet, and it damages our skin cells because the high energy and short wavelength mean that it can cause cancer for us as well. Infrared radiation is just below visible light, and it has actually a longer wavelength because it is less energetic. Humans cannot see infrared radiation, but we can feel it as heat, which is why you will often hear people say infrared equals heat. That's also how snakes can see their prey, because snakes have receptors that can pick up infrared radiation and assemble it into an image, the same way that an infrared camera would let us see what people are doing at night, even if our eyes can't really see what's going on. Most of the solar radiation reaching Earth is ultraviolet and visible light. Now, the sun is essentially pumping out the same amount of energy constantly. It's essentially a power plant that isn't going to have any variation in power. A few exceptions aside, sunspots are dark spots on the sun. They're relatively cool points on the sun, and if there are a lot of sunspots, that does mean that there is less solar radiation. So yes, there are some factors like sunspot cycles to factor in, but we will ignore that for now. We will assume that the sun is producing the same amount of energy constantly, and all parts of the sun are emitting the same amount of energy constantly. So that brings in a mathematical rule called the inverse square law. And basically what the inverse square law says is that if the energy source at the center is consistent, as you move out farther from the source, you're going to get bigger and bigger spheres. And when I think about and go from spheres to thinking about something else, elliptical, the orbit of planets, the orbit of Earth or Mercury or Jupiter. All of Earth, with a few minor exceptions, the planets are all on the same plane. They're flat, and there's other reasons behind that. But hypothetically, the sun could be surrounded by a sphere. So you can think of the different lines of orbit that those planets have as being parts of those different spheres. Mercury would have the smallest sphere because it's closest to the sun. The not planet Pluto would have a much larger one because it's much farther out. Earth has a specific, so there is a specific, what the point of this is that there is a specific amount of solar radiation that is reaching the Earth based on the inverse square law, which relates to Earth's distance from the sun. And Earth is in what scientists often refer to as the Goldilocks conditions, referred to as such because you don't have too much or too little solar radiation reaching the Earth. Mercury is not considered to be in the habitable zone because it is frankly being bombarded with too much solar radiation. It is getting intense radiation because since it is so close to the sun, the radius of the hypothetical sphere that includes Mercury's orbit has such a small radius that it's going to be getting just about as much sunlight as it would normally. Because you'll see what happens is that R0 is like the starting radius. As you get farther out, that means that you're going to be multiplying the starting amount of radiation by a fraction, by a small number. Multiply a number by a fraction, and it gets smaller. Since Mercury is so close to the sun, you're basically doing S equals the starting amount times R0 over R0. Mercury is basically the same radius as the sun, not quite, but I'm simplifying. R0 over R0 equals 1. You get about as much radiation at Mercury as you do if you're right by the sun itself. You move a little farther out from the sun, and you are in what astronomers consider the habitable zone, which contains Earth. If you go too much past Earth and Mars, you get to where Jupiter and Saturn and the other gas planets are. And at that point, the radius is so big that that produces too little radiation reaching those planets. The radiation is so spread out that it's essentially ineffective, and there isn't enough reaching the planet for photosynthesis to occur. So the outer planets, there's not enough reaching it, so no photosynthesis. The inner Mercury, there's too much reaching it at once, so it would simply kill whatever is there. On planet Earth, that's starting. So we have that set amount of solar radiation to work with. That's what we got. We would have to move Earth's position in the solar system to change that. Well, we would think that all of that energy would be usable for Earth. That is not the case. Only 48% of it actually reaches Earth's surface. 23% of it is absorbed by either particles or gas molecules in the atmosphere, and then 29% of it is similarly reflected by different particles or by different molecules in the atmosphere. The fact is that only about half of the solar radiation coming to Earth is even available for plants to do photosynthesis. And as we'll find out, this actually has consequences ecologically. There is a finite amount of energy that plants have available to use, and as it turns out, there is a finite amount of energy that plants can actually effectively convert into sugar for animals to then use. And spoiler, animals can only effectively use a small percentage of that energy that they eat. We will come back to that when we talk about ecology. Now, something I want to step away from, and I want to step away from that and talk for a moment about Malencovich cycles. I mentioned briefly the tilt of Earth's axis and how it varies over time, and that is just one of these 3 Malencovich cycles, it turns out. I mentioned that the amount of solar radiation reaching Earth is more or less constant, but if we're going to think in terms of tens of thousands of years, that's not exactly true. Earth's orbit is not a completely fixed shape. For one thing, in this hypothetical diagram of Earth's orbit around the sun, it experiences 2 extremes: a period of low eccentricity in which Earth's orbit is more or less circular, and then a period of high eccentricity. It's eccentric because it's squashed, it's weird, it's not circular, it's not square enough, but eccentric equals more ovoid. And during periods of high eccentricity, Earth gets actually a lot less radiation because it's farther from the sun for a lot of the time. And that does not actually directly have to do with seasons, believe it or not. But the eccentricity of Earth's orbit, so it goes from circular to oval and then back to circular over a period of 100,000 100,000 years. So not an enormous amount of time geologically speaking, but longer than any people are going to be alive. Meanwhile, I mentioned the Earth's axis, the tilt of Earth's axis change, and that is what's called the tilt or obliquity. And there is an angle formed between a hypothetical vertical line and the tilt Earth's axis actually has, and it will go like this over time. It will go from 21.5 degrees to 24.5 degrees and back, and here and back, over a period of 41,000 years. So not the same amount of time cycle as you have for eccentricity. The last of these is precession. And for precession, think of Earth like a top or a dreidel. If you spin a top or a dreidel, you'll notice that the little handle on the top or dreidel will kind of, even as it's circling around, the handle will point in different directions, and it'll kind of point in a circle separately from how the top or dreidel is rolling around on the ground. That wobble that you get from a top is really similar to what happens to Earth. The direction that, if you have like a hypothetical handle coming out of Earth's axis, the direction out into space in which that points changes over time. It goes in a circle over time on a scale of 23,000 years. So we have three separate factors that can influence the amount of solar radiation and thus the climate. None of these directly can be attributed to the climate change we are experiencing in the 21st century, because something catastrophic would have to happen for these to change on the scale of just a few years. It would be end of the world. These don't change on the scale of a few years. These change slowly on the scale of thousands of years, not in a way that humans can easily observe. However, climate scientists find Malencovich cycles useful because Malencovich cycles, it's possible to use a model to come up with a combined signal, use the three Malencovich cycles to determine roughly whether like an above average amount of radiation was reaching the Earth or a below average amount, which is what these negative and positive numbers mean for combined signal here. This diagram on the right is something we haven't talked about yet, but we'll talk about later. Oxygen isotopes, different molecular forms of oxygen, and how oxygen is present in a lot of things. So climate scientists are often want to see how these different forms of oxygen show up in, say, the shells of snails, or in ice, or in air bubbles. And some combinations indicate that you have ice, some combinations indicate that you don't have a lot of ice. It turns out that periods in Earth's time that have been well documented to have had intense glaciation during the last hundreds of thousands of years, the periods in which the combined Malencovich cycles gave less solar radiation correspond roughly to the periods of no ice. It's not an exact correlation, but Malencovich cycles play a role. Right now, we are technically still in an ice age. We are alternating between glacial periods of the ice age. So like that movie Ice Age is specifically, it should have been called Glacial Period, because we are still in the ice age. We still have polar ice caps, just not as big ones. We're presently in what is known as an interglacial period of the ice age, another term that we'll come back to, because there's relatively little ice right now. And it turns out that the variation between lots of ice, aka glacial periods, and not very much ice, aka interglacial periods, correlates to Malencovich cycles very well. Now, returning to infrared radiation, I mentioned previously that it's kind of like heat. Well, when a snake sees, in a sense, a mouse giving off heat like this, we are not luminescent bodies. We are not stars ourselves. However, there's a concept of a black body, and it's black because the hypothetical black body absorbs all visible light. The black color absorbs all visible light. But even a cast iron ball, a hypothetical black body, it can still transmit infrared radiation and other long wave energy. The thing is, if you heat up a black body, it will be more energetic. If you heat up a cast iron ball, it will turn orange and then white because it will be giving off higher energy light. But even if it's just sitting there with no heat underneath it, it's still emitting radiation, just not very much of it, infrared radiation. And the takeaway from this is that Earth, even though Earth is not a sun, Earth is not luminescent, there is still radiation coming from the Earth. What fundamentally happens is that the high energy, low wavelength solar radiation consisting of visible light and ultraviolet light gets absorbed by the Earth and re-emitted as infrared radiation or as heat. And this is where the greenhouse effect comes into play. The greenhouse effect involves the trapping of the greenhouse effect involves heat being trapped in Earth. So you don't have to memorize this diagram, but it's showing you that a lot of the energy doesn't reach the Earth's surface. About half of it does. About half of the energy gets absorbed by the land and the water and whatever's on it, like plants. And that energy has to go somewhere. It's processed, in a sense, by being absorbed by whatever it's absorbed by and re-released as infrared radiation. And a lot of that infrared radiation is going to escape back to space, which is fine, because too much of it is going to heat up the Earth and make it uninhabitable. Spoilers. However, if all of it escapes back into space, then you have an icehouse planet. You need some infrared radiation to remain in Earth's atmosphere to heat it up, it turns out. And what happens with greenhouse gases? A greenhouse gas is any type of gas that has the molecular properties to trap at least certain wavelengths of infrared light, and then emit that light back in all directions. Now, some of it will go back out to space, but then some of it will go back to Earth's surface and continue to warm the planet. And this is the greenhouse effect. Water vapor, carbon dioxide, methane, and other gases help the planet stay warm by sending some of that infrared radiation back to the surface. Now, if we didn't have this at all, we would have Mars. Mars does not have enough greenhouse. Mars is a dead planet for many reasons, but Mars does not have enough greenhouse gases to give it any insulation at all to keep it warm. And so whatever gets emitted by the planet just escapes back out to space, and Mars is cold. Venus actually has a runaway greenhouse effect. Venus has so many greenhouse gases that the planet is intolerably warm, and that is one of many reasons why Venus is not habitable. And I just have this here as a diagram to show you again, different things happen to radiation when it comes to Earth. Some of it's going to be lost via evaporation and convection, and then a small amount of it is going to be radiated back out to space, what you'd consider the net thermal radiation. That net thermal radiation will be stymied by greenhouse gases to some extent, and to some extent it'll go back out to the atmosphere. What controls this? The amount of greenhouse gas. How many greenhouse gases there are in Earth's atmosphere determines how much makes it back out to space and how much of the radiation remains in Earth's atmosphere to subsequently warm it. And we often think of Earth's atmosphere as being kind of just here, like I can wave my hand through the air and nothing's really happening, but we kind of take air for granted. Remember that I've talked about Mars and other planets that have a very thin atmosphere. We have an atmosphere that is breathable to us and that has enough greenhouse gases to keep the planet habitable, although we're playing with that presently with fossil fuels and the like. Now, the funny thing about the atmosphere is that over 3/4 of it is a gas that is completely useless to us, and that is nitrogen gas. Now, nitrogen is not useless. Nitrogen we need. Nitrogen is in DNA. However, when nitrogen is in N2 form, like two nitrogen atoms just joined together as a gas, they have a very strong chemical triple bond that is very hard to break. There are only a few microorganisms that produce the enzymes needed to break nitrogen gas. That is what's called nitrogen fixing, and peas and beans host the bacteria that do that, and we will talk more about that later. But most of the atmosphere is just kind of a filler gas. The oxygen that we need to breathe is only about 20% of the atmosphere. And when patients need oxygen, they are being provided a much more pure oxygen because their lungs can't get sufficient oxygen from the 20% in the atmosphere, essentially. That's why people need oxygen, because their lungs can't handle just 20% anymore, and they need to have more oxygen added. About 1% is argon, which is one of the noble gases and is thus going to interact with essentially nothing. Argon, xenon, helium are called the noble gases because chemically their electron shells are full and they will interact with very few other compounds, except under very specific circumstances. So that leaves a lot of other miscellaneous gases, including carbon dioxide, which you'll notice, in spite of all the talk about CO2 and its effects on the atmosphere, only presently takes up 0.037%. That is a tiny percent. So to deal with fewer decimal places, you can convert percents into parts per million. So parts per million is essentially just percent, but with million instead. And we have 370 ppm instead. Water vapor, which is also a greenhouse gas, overall makes up about 0.5% of the entire atmosphere, but at sea level it can be closer to 1% because there is a lot more water being evaporated at sea level. And even though water vapor is a greenhouse gas, it's not talked about as often because there is not a human-related activity that is dramatically changing the amount of water vapor. Although in different parts of the world, atmospheric concentrations of water vapor are being affected by climate change. So it's a secondary effect and one that has to be considered. Now chemically, Earth's atmosphere is about the same from one part to the other. However, physical properties vary. The physical properties of the atmosphere are very different. And we're going to talk about all of these layers, but we're specifically going to linger a lot on the stratosphere because of the ozone layer, the troposphere briefly because of weather, and then I'll talk about the thermosphere because it is where the aurora australis, as well as the aurora borealis, the northern lights, occur. In terms of whether you need to memorize these, you want to know what's going on in each of them and why the temperature changes that I'm going to talk about occur. So the main thing to consider is that these are all different layers that are separated on density. The amount of air particles per unit volume is different in all of them, drastically different. And it turns out that layers, whether layers of the atmosphere or layers of the ocean with dramatically different densities, do not mix very well. So the lowest layer of the atmosphere is the troposphere, which is where most weather occurs. In the troposphere, temperature decreases as you go up because you are getting farther and farther away from the Earth. And the closer you are to the Earth, if you're an air molecule, the more effectively you're going to be heated by infrared radiation. So the thing to consider is that even though solar radiation does drive atmospheric circulation, the infrared radiation actually does a more effective job of heating air. Air is kind of hard to heat up in a sense. It's very spread out. The infrared radiation from the much closer Earth does a more effective job of heating up the air. And so that means that the temperature drops from the bottom of the troposphere to the top of the troposphere as you get farther away from the Earth. So this is why you have storms and hurricanes and tornadoes all occurring within the troposphere. It all has to do with for the most part, has to do with variations in the amount of infrared radiation being radiated back from the Earth. And I want to briefly talk about what weather is versus climate, because climate relies on big pictures in a way that just talking about the weather doesn't. Climate involves taking averages of temperatures, rainfall, air pressure, and the like, and also thinking about how that's going to vary over the course of a single year, how that varies seasonally, and giving a big picture as to what the climate is like. Does the average rainfall indicate that you overall have a rainy place compared to other parts of the world, or compared to this part of the world at a different point in geologic time? Climate allows us to make comparisons. Climate, because it's based on averages and ratios, allows us to compare different places or the same place at two different points in time. The weather for a single day is like a single data point. I like this diagram because the curve itself is kind of like the climate. It's going to produce a broader sense of what the temperature is like each year, and it is based on all of these individual low temperature points and high temperature points that were taken each day. And you need those data to get a picture of the climate. But the weather is going to be either the data for one day or your prediction as to what the temperature or humidity or wind is going to be like the next day based on the data you have for today. Climate is based on an average of weather over time. I really like the quote of climate is what you expect based on your data, but weather is what you get, because it does a good job of explaining how you can have a place with a dry climate like Tucson, Arizona, but it'll get monsoon level rains a couple times a year. And so you can't deny that it rained a lot on those couple of days, but if you look at the rainfall for the entire year, it's not going to be a wet place. You're going to have a couple of brief periods of torrential rain counterbalanced by extreme drought. Moving on from this realm, once we get out of the realm of weather, we get into the stratosphere. And the stratosphere is mostly notable because of the ozone layer. Now, the ozone layer actually is why the temperature rises again. As you enter the ozone layer, you have the ozone molecules themselves being continuously destroyed and recreated in a process that releases a lot of energy and heats up the air as you go higher. So in the troposphere, the temperature change has to do with distance from the Earth. In the stratosphere, it has to do with the amount of ozone and how close you're getting to the ozone layer. And the ozone layer is kind of in the upper part of the stratosphere. The ozone layer itself is made of oxygen-3. Oxygen-3 is what you get when instead of 2 oxygen molecules, you join 3 together. And O3 and O2 will be constantly driven in this energy cycle by the energy from the sun. What happens in the stratosphere is that ozone accumulates. Ozone is actually a pollutant if it's down in our level in the troposphere. You may hear the term tropospheric ozone, and that is smog. Ozone can cause smog. However, for the most part, it rises and accumulates in the stratosphere, and it forms a layer that is going to be thickest around the poles because the air gets funneled to the poles by air circulation patterns. I mentioned the poles are high pressure zones, and that means that air is being funneled to them by and large. We'll talk about that during the next lecture, actually. But ozone is measured in terms of thickness, and it's hard to really measure the thickness of a gas because its properties change so much depending on the temperature and pressure. So scientists invented a concept called the Dobson Unit. A single Dobson Unit is how thick the ozone would be. The ozone would be 0.01 millimeter thick if you were at standard temperature and pressure, 0 degrees Celsius, 1 atmosphere of pressure. This way, so what this does is that you can figure out how thick the ozone is and measure the temperature and pressure and get a Dobson unit from that. And you can then compare ozone concentrations in different parts of the world where the air pressure is different or where the temperature is different. And what the ozone layer does is it stops a lot of ultraviolet radiation from reaching Earth's surface. The ultraviolet radiation gets used up, either destroying ozone molecules or putting them back together. It's kind of a cycle. You have this replenishment cycle of ozone being destroyed, turned into O2, and then being turned back into ozone from interactions with another O2 molecule, and you'll have loose oxygen molecules being released to continue this cycle. And it's kind of a buffer. The ozone sort of takes the pounding for us and means that a lot of this ultraviolet light gets turned into thermal energy instead, and a lot of ultraviolet light that would reach the Earth's surface and kill amphibians and cause cancer doesn't make it. However, human activities have depleted ozone worldwide, and this is the ozone hole that you may have heard about. Ozone can be broken down by compounds containing the halogen elements, the ones right next to the noble gases on the periodic table. Unlike the noble gases, chlorine, fluorine, bromine, and iodine to a lesser extent, they're short one electron, and they're usually going to be have one extra electron, that they are going to be, to anthropomorphize them, they're going to be very willing to give that electron to react with something else. Fluorine compounds tend to be very reactive, so do chlorine compounds. Well, aerosols such as this, various sprays, mousses, it's not the product themselves, but the product themselves are going to need a carrier gas to get them out of the can. Those carrier gases for a long time were CFCs, chlorinated fluorocarbons. They were also used as refrigerant cooling gases. And naturally, these gases escape from the aerosol cans and from the refrigerators, and they are long-lived. CFCs are quite long-lived, and they will eventually bide their time until they are, just as ozone is, accumulated towards the poles. Atmospheric circulation causes them to accumulate in the same place that ozone is accumulating. These will then begin to interact with and react with the ozone, breaking it down and not replenishing it because they don't have oxygen in them, or at least they don't give them an oxygen the same way that an oxygen molecule interacting with ozone does. The other compound that does this, aside from CFCs, are NOx compounds, NO2, NO3, and those are largely from jet emissions. So human gas emissions produced a lot of these compounds that are going to interact with ozone, and weather caused them to accumulate, or excuse me, atmospheric circulation caused them to accumulate above the North and South poles, especially the South poles. What makes it worse is that the reactions in which CFCs destroy ozone go faster under cold temperatures. And because they're so long-lived, CFCs can destroy thousands of particles of ozone and make a noticeable difference. What happens in Antarctica is that we have a zone of depletion. There's not no ozone period, but if you drop below 2020 Dobson units, you don't have enough ozone. You are going to get a noticeable amount more of ultraviolet radiation reaching the surface, which you really do not want. Now, it becomes noticeable in August because August is right after the winter. During the winter, no sunlight reaches Antarctica, and a strong circumpolar wind develops because you have such low pressure. This forms in the stratosphere, where the ozone layer is, and essentially isolates the very cold polar air above the continent. And it also traps any CFCs that are in there and stops ozone from elsewhere from replenishing the ozone hole. So not only can CFCs wreak havoc, but when it's really cold, below 80 degrees Celsius, you can get polar stratospheric clouds. Nitric acid, one of the culprits that's released by jet engines, can form this thing called nitric acid trihydrate when you have large droplets of water ice forming with nitric acid. And this can destroy even more ozone. These polar stratospheric clouds can form and deplete huge amounts of ozone. These clouds are not made of water, they're made of this nitric acid thing. And this usually after August and September, the hole will start to fade because as the polar vortex decreases in strength and the summer passes along, ozone from elsewhere in the world will start to replenish the hole. But you have the hole to begin with, and that is a problem because too much ultraviolet radiation can cause cancer. It can also kill plants and either reduce crop yields, or in the Southern Ocean, something we'll talk about later, is that the food chain is based on plankton that do photosynthesis. Too much ultraviolet radiation will kill them, and fewer plankton mean fewer crabs and other animals to feed on them, which means fewer penguins and whales. Ozone depletion is often cited as a success story and kind of a template for climate change because there's a lot of eerie similarities with what happened with it to what is going on with the political discourse with climate change today. A study in the 70s indicated that CFCs were going to cause ozone depletion, and most other scientists, including the ones who peer-reviewed it, the unrelated scientists who looked over this to see if their methods were accurate, they thought, okay, this seems accurate. However, the industry did not want to suddenly have to shift to making a bunch of new methods, and they started drumming up public opposition, getting think tanks to call CFCs a lie, publishing papers that were not peer-reviewed, saying that CFCs and ozone depletion were a myth, just like we have happening with climate change today. The ozone hole, however, was kind of a wake-up call. Some British scientists discovered it in 1985. And 2 years later, the most industrialized nations on the world ratified a protocol that would phase out CFC production heavily and completely cease it by 2030. And I believe the European Union countries have already completely ceased CFC production. And this appears to have helped. The hole has begun to seem less pronounced and has not been getting bigger. However, it must continue to be monitored. And I do think that one reason why this might have been an easier problem to tackle than climate change might be that as ubiquitous as refrigerators and CFCs as aerosols and planes are, there's not quite as many things that depend on CFCs as do depend on fossil fuels for production right now. And the companies are putting up a much bigger fight now, I would say, because so much infrastructure, so much of society has been built on fossil fuels, and they don't want to do the work they don't want to do the work that it takes to fix that. It is admittedly a much more bigger undertaking than replacing CFCs. It must be done, and they need to do it, but they don't want to. The mesosphere is where meteors burn up. As you get farther and farther away from the ozone layer, it gets colder again. The remaining gases get very heavily stratified based on their mass. And what happens in the mesosphere is that's from the perspective of a meteor or a falling star, that's where the air is first thick enough to cause air resistance. That is where the air resistance actually destroys these things that have been flying through space, because remember, there's nothing in space. There's no atmosphere in space. Space is a vacuum. Above that is the thermosphere, where you have an interesting paradox of extremely low density of gas, but because you're right where the solar energy is hitting the Earth, right where the solar wind is hitting the Earth, those few gas particles that are present will get very heavily sped up by the radiation. Like the heat equals fast particles. It's like if you heat a balloon up, a hot air balloon. The gas particles will have a very long time to travel before any of them hit each other. And when they do hit each other, they will release a lot of energy. So that is why the thermosphere is called the thermosphere, because this low density air paradoxically leads to some very intense air particle collisions. In the exosphere, kind of the boundary lane, that's where gases start to escape into space. This is where the aurora happens. This is where the southern lights happen. Now, yet another sphere I want to mention, not to do with the atmosphere, is the magnetosphere. It is the region in space that is affected by Earth's magnetic field. And the aurora borealis or the aurora australis, depending on what side of the Earth you're on, is an interaction between Earth's magnetic field and charged particles. You have an interaction between electrons, the negative subatomic particles that are being driven by the sun. The solar wind is essentially fast-moving electrons from the sun. Those will interact with gas molecules in the atmosphere. And for the most part, Earth's magnetic field deflects a lot of these electrons and stops much of this interaction from happening, which is good because constant solar bombardment would destroy Earth's atmosphere eventually. At the poles, however, something you'll notice in diagrams of Earth's magnetic field is that the lines of Earth's magnetic field they're straight up and down at the poles. They kind of converge into the north and south magnetic poles. And it is easier for solar wind particles to enter the outer reaches of Earth's atmosphere here. What this means is that at the poles, where Earth's magnetic field is oriented in a way that it's easier for the solar wind to get in, you have a lot more of these flare-ups. You have a lot more of this flashing caused by essentially gas molecules being excited by these electrons, being, in a physical sense, being excited and put to a higher energy state. And that's what this flash of light is, and why you get these beautiful patterns of light in the polar skies, because it is a reaction. It has to do with the relative weakness of the magnetic field at the poles. And something else to consider is that Earth's magnetic field changes over time. There are times when the northern or southern lights have been documented to change. And where they're visible from seems to change with Earth's magnetic field. Earth's magnetic field does undergo some large-scale changes that we'll talk about in a different lecture. So that's the first part of this lecture. We will continue on to circulation next. One thing I want to mention is that there are a couple of short articles to read this week on gaucho space. There is also an excerpt from Frozen Planet, a documentary made by the BBC about the poles. The episode has stuff on both the Arctic and the Antarctic, so I gave you a time window on gaucho space of what to watch. You can skip everything else except if you're interested. So resuming with the second lecture coming up.